Okay, so this is a recorded video for the potential layer part. Okay, so we stop here, maybe here, right? Okay, so um, to measure the similarity between the quality vectors and input vector, one of the input vector, xi, we just use the scale dot product q xi over square root of dq equal to ei. Then after software function, we are going to finally estimate the y, that weighted sum of the input vector x. Okay, so next generalization of the attention layer is rather than just one quality vector, from now on, let's talk about the NQ kinds of different quality vector. So from now on, we have NQ by DQ quality vectors and NX and DQ, NX by DQ input vector X, right? So in this case, we can similarly compute the similarity between the quality vectors and input vector and define the attention and generate the output. But compared to the single case, from now on, we have to consider similarity between each element. Let's say qi and xj. Let's say xj, and generate the ei comma j. Of course, this dot product is normalized by scale of the dq, length of the dq, right? Dimensionality dq, and so because this is a matrix, right? This matrix, so final matrix E can be effectively computed by matrix Q times X transpose over square root of dq. So, because we consider now say element by element similarity between Q matrix and X matrix, then our final similarity map is going to be the E, which is equal to Q times X transpose over square root to dq, where the size of E is going to be NQ times NX, because we have a NQ kinds of quality vectors and X kinds of input vector. Of course, we need a subtract function to normalize this similarity matrix A, E to the A attention map, where the normal subtext dimension should be dimension 1. In this case, right, if we have the E matrix E, NQ by NX, similar to the single case, softmax should be applied to the this axis, right? I mean NX axis. So this is a dimension 1 because the the NQ axis means the dimension equal to 0, right? Okay, after that, y, our final y is going to be the A times X, original matrix X, input matrix X. So, because the A, matrix A, size of matrix A was the NQ by NX, and matrix size of matrix X was the NX times TQ, right? Sorry, in this case, the TQ or TX, right? Exactly same, TX or TQ. Then, your final y, size of y is going to be the NQ times the dx, which means NQ kinds of quality vector generate corresponding dx dimensional output vector. Right? Of course, this one is a weighted summation of the xj based on the ai comma j. So this is a vector form of the quality vector case. Okay. So our second change was for the generalization of attention layers. We just use the scale dot product for the similarity, and multiple quality vector can be considered. Okay, so that's it. But in more general case, maybe quality vector and x vector will be different. I mean the size of the dimensional array q and x will be different as a dq and dx respectively. So, and another problem is, okay, here, as you can see here, to compute the similarity and to generate the final output, same input X is used. But in many cases, optimal matrix for the similarity measure and optimal matrix X to generate the final output would be different, right? So to compensate this, from now on, we will introduce the key matrix and value matrix, which project original matrix X to the K and V, key vectors and value vector. So more specifically, this K vector is just used to measure the similarity between query vector and input vector X. Rather than considering the input vector X directly, this key vector may be the better feature embedding for measuring the similarity between Q and K. So we have some flexibility, and because this is a learnable part, if we can find the optimal key matrix, let's say WK or WB, maybe your performance will be maximized. Because this is just like matrix multiplication, so this is kind of MLP module, and of course this is a learnable module. Then you can just compute the similarity between each query vector, each X vector, right? And just apply the softmax function, and to measure the final output Y, rather than considering the X directly, from the here we just used value vector, which is the projected version of X with a linear projection layer W, right? So rather than directly using the X, this V vector is the learnable embedding output, right? Which means with good loss signal, your attention layer will generate a much better performance, right? Okay, so this is the key vector and value vector. The third one is third change is separating key and value. Okay, so right. Okay, let's summarize what we've done so far. We have a query vector, set of the query vectors, right? And we have an input vector. So I would say this is not just input vector. Let's say something like target vector or a candidate vector. Because in many cases, query is kind of input vector. So you may confuse to say this is X. X as a input vector. So let's just say X is a target or candidate vector, and query is the real input vector of the attention layer. Anyway, given query vector and X vector, Q and matrix Q and matrix X, first of all, just embed X to the K vectors by using K matrix. So, right. After that, right. So this is the embedded X vectors, right? After that, just measure the similarity between Q1 and K3, Q1 and K2, Q2 and K3, Q3 and K3, blah, blah, blah. So you are going to make a matrix E here. Of course, you need to normalize the similarity by square root of DQ. Okay, this is a similarity map between query vectors and input vector. Okay, then after that we need attention map. How can you do that? Just normalize such a E matrix to the A matrix. Please be careful when you apply the softmax function, because the we have to normalize this similarity map across this dimension, right? Because this dimension means the set of the target vectors, let's say x. So just normalize E1, E1 to E13 to generate A11, A1 to A13. So it means that some of these three vectors should be zero. 계속 헷갈리네요. 아니, 1이에요, 1. 자, 수업 시간에 계속 헷갈리는데 1, 그죠? A1 plus A12 plus A13 is equal to 1. And EJ, which means A vector, A value is less than 1, larger than 0, right? Okay. Okay. And, sorry, A could be negative value, but it should be larger than negative 1, sorry. If you are not normalized input vector. Okay. Because this is unprotected, right? Right. So after that, we want to finally generate the corresponding output given query vector. So we just project, embed or project x1, x2, x3 to the v1, v2, v3 by using value matrix or value MLP. Then, right, finally, just compute the weighted sum of the A11, A1 to A13 given V1, V2, V3 as a weight. Then, we compute the weighted sum of the V1 and V2 and V3 given A11, A1 to A13 as a weight. Right, 3. Okay, so after that, your Y1 it's going to be A1, 1 times V1 plus A1, 2 times V2 plus A13 times V3. Right. So similarly, you are going to compute the Y2 and Y3 and Y4. Okay. So to sum up, given 4 kinds of query vector, you just estimate corresponding output Y1, Y2, Y3, and Y4 given X1, X2, X3 candidate vector or target vector. This is a generalized version of the attention layer. So before moving, please directly compare this attention layer, generalized attention layer, and previous such a short antenna model. It has a good analogy between them. Okay. Right. So because this is a recorded video, if you have a question, please let me know via email. Right. Okay. This is the channel. So, in other words, from here to here, we are going to say this is a kind of attention layer where input of this layer was matrix Q and X and output was Y, right? This is the general formulation of the attention layer. Okay, then what about self-attention layer? What about self-attention layer? Self-attention layer. So, self-attention means you don't have any additional query vector and target vector X, but in many cases, this query vector and target vectors are exactly the same, right? Then your only input for the attention layer is going to be the matrix X, set of the vector, right? X, which means rather than setting the extra vector set of the vector X in self-attention layer, your vector X is going to be the key query value at the same time with corresponding MLP layer like key matrix WK, value matrix WQ, and query matrix WQ. So in other words, from now on, your query vector is going to be the Q is equal to X times to WQ, where WQ is the learnable parameter. 러돌 매트릭스 운론을 바랍니다. And similar to the previous slide, key vectors is going to be the k equal to x times wk. And value vectors is going to be the v is equal to x times wv. Then similarly, E is going to be the q times k transpose over square root dq. Square root dq. And A is going to be the softmax of the matrix E. Y is finally going to be A times V. To sum up, we only have the input vector X, similarly to convolutional neural network or other neural network. But we just embed input vectors x1, x2, x3 to the q1 to q2 to q3 with a query matrix or query MLP and k1, k2, k3 with key matrix or key MLP. Then measure similarity E, right? Then estimate the attention map, and X is further embedded to the V1 and V2 and V3 with a value matrix or value MLP, and finally, your corresponding output Y1, Y2, Y3 is going to be V1 times A11 plus V2 times A22, V3 times A13, right? Then here, from here to here, we only have a input vectors and corresponding output vector. So from now on, let's say this is the self-attention layer. And this is a generalizable layer. So you are going to understand the interaction between x1 and x2 and x3 or x2 and x3 blah 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 by using such a attention mechanism, and maybe these kinds of layers will generate much better performance compared to the original convolutional neural network or the CNN neural network. Okay. So this is self-attention layer. So from now, let's talk about properties of the self-attention layer. First of all, okay. So when we carefully look at such a attention mechanism, there is no way to understand the order of the sequence, right? Because when your original sequence is x1 to 3, if we just permutate x1 to 3 as x3, x1, x2, then self-attention mechanism will be exactly will be applied to the such a permitted input, but interestingly, query and key will be same but permitted like Q3, Q1, Q2, K2, K1, K3 because it's just like the MLP module, 그죠? Produced by MLP. MLP just apply to the element vector-wise independently, and similarly will be same but permitted, right? And attention wave will be same but permitted. Value will be same but permitted. Finally, your output will be same but permitted, right? So, second layer is permutation equivariant. It means that if we just say matrix f function is the self-attention layer and S is the permutation operation, output of the self-attention layer of the permitted input is equal to permutation of the output of self-attention of original sequence of input X. So permutation equivalent each other. So which means self-attention layer works on set of the vector. Just set of the vector. So we don't have any meaning of the order. Right? So this is the say properties of the self-attention layer. So to sum up, self-attention doesn't know the order of the vector it is processing, right? Within their module. But in many cases, order of the sequence was the one of the important issues to understand the context of the SQL data. For example, like the language in English, right? So if if we just permute the word, order of the word in the one sentence, maybe the meaning will be different, right? Okay, to compensate this, or in order to make a processing position aware, in self-partition layer, we often concatenate or add position embedding. Let's say position embedding, or which is called the PE. So position embedding is literally position embedding. Position embedding. 그러면 okay, here. So as we discussed in previous slide, in this case, x1 was the tx by one vector, right? So there's so many kinds of way to give the position information, information. First of all, x will be the one kind of vector. Then it's going to be concatenated to the original vector. Or if the dimension is the same, and then we can just add each other. And this making position embedding. And to make position embedding, there are so many kinds of way. First of all, it can be just learn. It can be the learn the lookup table. For example, okay, just randomly initialize during the training these vectors and just fine tune or update these random initialization. Then we can just say it shows the position of the each vector x1, 2, 3. Another very interesting idea was fixed function. Because this is just like the sequence, right? So we can just say this is the first one, second one, third one. Then by using the some predefined function, for example, sinusoidal or the sinusoidal. You can just predefine such a position embedding. So there's so many kinds of way to make a position embedding, which allows to know the order of the input sequence within self-partition layer. Okay, this is position embedding. Another variant of self-partition is masked self-partition layer. So masked self-partition means, in many cases, we don't want to. We want to vectors doesn't look ahead in the sequence. So which means, for example, when you just go back to the language generation here, maybe you can just set sequence of the query vector and estimate of output directly, but in what sequence generation case, thus say sequentially generating is a really important issue, right? Because this is a word. The sentence. So to model such as say processing properties within self-partition layer, masking technique is popularly used. So what does it mean? So implementation of the mask self-partition is really simple. Right. Just mask out off diagonal, the upper off diagonal term as a zero. So in this case, in this kind of off diagonal, the off diagonal zero attention matrix case, the up y1 from x1 only related to the v1 from the x1, right? And y2 only generated from v1 and v2 because we only have the a1, 2-1 and a2, y3 is decoded, can be decoded from the a31, a32, a33 with v1 and v2 and v3, right? So don't let the vectors look ahead in the sequence, right? So each vectors given set of the vectors x1, x2, x3 each sequence vectors only relies on previous sequence vector. Okay. To make optimal determinant 0 after softmax function, we're going to set negative infinity on similarity map. Right. So such a mask self-attention layer is popularly used attention-based decoder for generating the language or the sentence information, similar to the previous example. Right? But implementation is very, very simple. Okay. Right. It's often used for the language modeling to predict the next word sequentially. Right. Last one is a multi-head self-attention. This is another variant, right? So IDEO is very basic. I mean, the IDEO is so highly similar to the Google Lab. Right. Let's suppose that you have the set of the vector x1, x2, x3, and in this case, each vector dimension was the dx. But similar to the Google Lab, inside each channel, each channel may be processed independently with independent self-attention module. Then, in multi self-attention layers, we use the H independent attention head in parallel, like this. First of all, just split the channel of the input vector x as a H kinds of independent one. In this case, H equal to 3. So, each vector dimension is going to be dx over 3. dx over 3. Right. Given such a separated vectors, just apply here, given set of the vector, set of the separated vector, just apply self-attention layer x1, x2, 1, x3, 1, and x1 to x2 to x3 independently. So they are not shared. They are independently trained self-attention module. And of course, because this is self-attention layer, you are going to estimate y11, y2, and y31. I mean, we can run self-attention in parallel on each set of the input vector. Different weight for each head. Then, because each coming from these three different kinds of feature vector were coming from the original vector x, right? Then, finally, just concatenate y11, y12, y13. Please note that dimension of y11 still dx over 3, and input of self-attention vector was dx over 3. So please note that dimension of the input and output of the self-attention layer is actually same due to the design choice here. So please be careful when considering dimensionally. Okay. Sorry. So by now, so far, the length of the dimension of the input and output vector will be different. It's allowable. It's allowed in self-attention layer. But in transform layer, we have a strict constraint between the dimension of the input and output. But in self-attention itself, there's no such a constraint. Anyway, but still, these three output coming from the three separated feature map, it should be concatenated to generate the final output. Then finally, because they are separately considered, this one is finally projected with the additional MRP to generate y1, y2, and y3 from x1, x2, x3. Right? This is the multi self-attention. Okay. So let me briefly summarize this one. 보면 한국말로 한 3분, 5분 정도만 설명을 다시 해볼게요. 그래서 어텐션 레이어를 제너럴라이즈 하는 게 우리가 이제 x로 시뮬러리티도 찾고 밸류까지 곱해서 y까지 하려고 하니까 너무 힘드니까, 그러니까 옵티멀이 아닐 것 같으니까 우리는 러너블하게 WK와 WV를 넣고 그 MLP로 설계해서 x를 K와 V로 떨어뜨려서 QK 가지고 시뮬러티를 재고 밸류로 파이널 아웃풋을 내는 이런 식으로 하면 조금 더 잘 되더라 라는 게 이제 알려져 있었고요. 근데 그러다 보니까 그걸 이제 쭉 방금 설계했던 얘기를 하면 이제 이렇게 돌아가는 거죠. 이거 자체 이제 우리가 어텐션 레이어라고 제너럴라이즈 할 수 있어요. 근데 그러다 보니까 또 많은 태스크에서는 이런 X라고 하는 인풋이 추가적으로 필요하지 않을 경우도 있어요. 그러면 이제 그러니까 X를 가지고 쿼리 자체도 만들어 버릴 수도 있죠. 그러면 우리 이제 쿼리를 만드는 쿼리 매트릭스 WQ를 가지고 X부터 K를 만들고요. Q를 만들고요. 그래서 QKV를 가지고 시뮬러리티 잡고 소프트에 돌려서 Y를 뱉어내는 과정을 거치게 된다. 이게 이제 바로 셀프 어텐션 레이어였다. 그리고 이게 이제 바로 트랜스포머의 가장 싱글 빌딩 블락이 되는 레이어였다 라는 얘기를 하는 거죠. 그렇죠? 그래서 이제 열심히 이렇게 해보면 쭉쭉쭉 해보면 이제 이렇게 설계되는 거고, 이게 결국에 어떤 X 벡터가 3개 들어오면 Y 벡터 3개가 코리스판에 나오는 이제 하나의 어텐션 레이어다 라는 거고, 이게 MLP처럼 그냥 동작하는 건데 기존 MLP나 어떤 그 CNN보다 더 잘 되더라 라는 거죠. 그래서 이제 특성이 퍼뮤테이션 인베리언트 했고 막 보면은 그렇게 될 수밖에 없이 설계되어 있죠. 근데 그럼에도 우리가 이제 포지션이 중요한 태스크들은 있어요. 그런 경우에는 포지션 인베딩을 강하게 넣어서 인코딩을 넣어서 이제 포지션 정보를 넣고 해주면 퍼뮤테이션에 이퀴벌런트 하지 않게 만들고 포지션 어웨이하게 할 수 있더라 라는 것도 있었고요. 그리고 셀프테이션의 많은 베리언트 중에는 이제 마스크 셀프테이션 같은 경우는 요 어퍼 오브 블락 다이아고널 텀을 다형으로 만들어 버리면 강하게 x1을 할 때는 y1을 할 때 x1만 보고 y2를 할 때 x1, x2만 보고 y3를 할 때 x1, x3만 보는 이제 이런 텍스트를 디코딩 할 때는 이런 식으로 셀프테이션 그냥 쓰면 안 되고 이렇게 시퀀셜하게 프레이션 해야 되는 마스 셀프테이션을 쓰면 된다. 하지만 여기만 강하게 그냥 우리가 영어로 만들면 되니까 거의 구현은 완벽하게 똑같더라 라는 거죠. 마지막이 이거는 사실 경험적인 발견인데, 이 DX 채널을 한 번에 어텐션을 태우는 것보다 얘를 어떤 H개로 스플릿을 해가지고 이렇게 쭉쭉쭉 스플릿을 해서 각각을 완전 다 독립적인 셀프테이션으로 각각 돌려서 Y를 딱 만들어내고 얘를 그냥 다시 컨캣한 다음에 한 번 그냥 MLP 그냥 우리가 구글에 했던 것처럼 이렇게 태우면 학습이 좀 더 잘 되더라. 그래서 사실 이 멀티헤드 테크닉은 디폴트로 거의 쓰여요. 그렇죠? 그래서 이제 이런 셀프텐션 레이어가 이제 우리가 갖게 되었더라. 그래서 MLP, 그치, 뉴럴넷, 셀프텐션, CNN처럼 그냥 하나의 레이어 쪽으로 우리는 이제는 이걸 쓸 수가 있게 되었다. 많은 경험적 파인딩에 의해서. 그리고 이렇게 잘 설계된 모듈을 이제 우리는 갖게 되었고, 이거를 열심히 조합을 잘 시킨 게 결국에 이제 우리가 이와 가장 또 중요한 파트 중에 하나였던 트랜스포머 구조가 여기서 나오게 됩니다. 알겠죠? 또 제가 이제 오늘은 레코딩 비디오라 빠르게 좀 지나갔는데 여러분 천천히 한번 복습해 보시고 제가 하는 말들을 잘 곱씹어 보시고 질문 있다면 우리 편하게 온라인으로 주고 우리 다음 시간에 봅시다. 네, 수고하셨습니다.